talk about trusted operating system design. And you'll notice the word is trusted and not secure. So why do we talk about trusted OS rather than secure? That's because secure is sort of a binary idea. Either something is or it isn't secure. And nothing is secure. So by saying, oh, it's a secure operating system, that implies a kind of perfection that doesn't really exist in practice. So people use the word trusted because trusted implies I trust you until X happens, or I trust you for this purpose but not for that purpose. Trust can also be context dependent. So I trust it, but there may be some reason that you don't trust it. So that's why we talk about trusted OSs. You should understand there are standards for trusted operating systems that specify how the computer must operate. I'm not going to ask you about this, but if you're curious about what it means for something to be a trusted operating system, you can read about some of these things online. Again, I don't expect you to understand specific standards by names. I do think you should know that FIPS is the Federal Information Processing Standard, and that's the security standard for government hardware and systems. But what I do expect you to understand that there are standards that exist and may be required for certain circumstances. So if you want to sell, a tamper-resistant, hard drive for the government, that's going to have to meet a certain FIPS standard for that purpose. All right, next idea is completeness and correctness. And completeness and correctness mean essentially what you'd expect them to mean in the normal world. So completeness means everything is handled. So in this case, every security vulnerability or issue is covered in some way. And correctness means that for each thing that you handled, you did it correctly, right? So things have to be complete and they have to be correct in order for them to be trusted. One thing where completeness and correctness really matters is this thing called a reference monitor. And we talked about this before, but the reference monitor is one piece of code that handles all of your security checks. The properties it needs is that it's tamper-proof, unbypassable, so you can't skip it, and it's analyzable. It must be complete and correct, right? If you have a reference monitor that handles all your security checks, but it's not correct, or it doesn't handle all of the cases, then it's not a very good security reference monitor. And again, a reference monitor is something that is useful beyond operating systems, but for any large application. So my pen is still broken for some reason. I thought I had it fixed and now it's broken. But imagine I have some operating system or some large software system that has a bunch of different components. And those components need access control or have permissions around them. And over here I have a user. I'm drawing with my mouse, so it's not the best. So a reference monitor is essentially a big box that goes around all the components of the system. So if the user wants to make a request, okay, the reference monitor is a thing that is going to evaluate that request and either accept it and allow the user to access the thing that they want, or the reference monitor is going to deny that request and say, no, that's not allowed. And the point of a reference monitor, again, it's tamper-proof, unbypassable, and analyzable. That means that you just have to make this one thing, and then it's going to handle all your security checks. Okay, so that's the value of a reference monitor. You create that thing. I don't need to make security code for each of these systems. It might have different code. Maybe I forget to update the code on one system. We just make one reference monitor security system that protects all the relevant components. Every access has to go through that system, so it will either be allowed or rejected. So that's a reference monitor. It's essentially a way of putting all your security code into one thing that you reuse. Okay, another important idea is called a trusted path. And it's easy for humans to identify and authenticate ourselves to a computer, right? Usernames and passwords, for example. But how can the computer identify itself to us? And this is a major security issue. And by computer, I don't just mean the computer itself, but I mean the operating system or a particular app, okay? How can it identify itself to us? I had a friend in college who used to go into the computer lab back when it was OS 9 and there were no permissions systems on there. And he would take a screenshot of the desktop with nothing running, and then he would set the wallpaper of the desktop to be that screenshot of nothing running. And then he would hide all the icons by pushing them off to the side of the screen. So anybody who sat down and tried to use the computer couldn't, because they'd try to open the programs or interact with anything on the desktop and nothing would happen, because there was no way for the user to identify that they were actually using the OS and not just interacting with a wallpaper on the back of the screen. So spoofing, essentially he was spoofing the OS with a wallpaper, and that made it really hard to understand what was going on. So the computer didn't have a trusted path. And Windows uses Control-Alt-Delete to initialize a trusted path. So originally Control-Alt-Delete rebooted the computer, and only the operating system could catch that keystroke to stop it from happening. So no user application, user privilege application could catch Control-Alt-Delete, only the OS could. So at some point in Windows, maybe Windows 10 or Windows 7, actually no, it was much earlier than that, Windows NT, Windows XP, instead of rebooting the computer, Control-Alt-Delete brought up the Windows Task Manager or login screen. And so since no program could do that, if you press Control-Alt-Delete, no user program could catch that and pretend to be the operating system. You knew that if you pressed Control-Alt-Delete and you got the login screen or the Task Manager, you were actually dealing with the operating system, okay? And so that would let you log in, run the Task Manager, kill programs, or expose a spoofer, because the OS couldn't actually do that. Because a spoofed app could not do that, I mean. Another part of the trusted path in Windows are these dialog screens that are brought up by the operating system. So to tie these two ideas together, if you see these kind of dialogues in Windows and you're like, I'm not even sure if this is Windows or if this is a program pretending to be Windows, well, press Control-Alt-Delete and you'll find out if you're actually dealing with the operating system or if you're dealing with a program pretending to be the operating system. So in any trusted system, you need to have a trusted path by which that system can identify itself to the user. Another really important idea in trusted systems is signed code. So we've mentioned this a few times in the class, so I'm not going to go into a lot of detail here. But basically, back in the day, you would just download software and install it, and you hoped that it actually came from the person that you thought it was from. But now, virtually all major software is signed using the private key of the software creator or distributor. So when you try to install it, for example, in Windows, you get a thing that pops up and says, hey, this is from such and such a company. Do you really want to do this? Do you want to trust them? Install it or don't install it. And that is because, again, that code's been signed by the publisher's private key. You verified it using their public key, and that way you know that it's actually from them. Basically all software from app stores that you buy online, distribution from, say, Linux distributors or whatever, that's all signed. If you're installing software that's not signed, you kind of have to ask yourself, why isn't this code signed? Now, to extend that idea, modern machines support something called Secure Boot. And in Secure Boot, everything about the boot process is signed. Okay, so and the hardware on the motherboard itself verifies that signature. So it works something like this. So when you try to boot your computer, this module is called the TPM. The TPM checks the bootloader, and the bootloader is this tiny little program that starts to load your operating system. And it verifies the signature or it quits, okay? If that works, then that code loads the next piece of the OS and verifies its signature. Okay, and if that works, it does the next piece and so on. Finally, you get into a signed and verified OS. Okay, so again, this idea is you turn on your computer, you don't want it just loading any operating system. You want to make sure that it's loading your real operating system from your real OS provider. So the TPM is going to check the first tiny little program that it loads to make sure that it's actually the signed one from Microsoft. And then the next piece will check a signature and the next piece and so on. And so what you have is this chain, okay, of signed OS code. So you know that at each stage of the operating system, you have the correct piece of the OS, okay, and that it's actually a signed operating system. Okay. Another critical idea in trusted systems is something called the trusted computing base. And basically, if you take all of the code and apps and things that run on your computer, you can divide that system into two parts, okay? One part is called the TCB, or the Trusted Computing Base, and the other part is not the TCB. Okay, so I'll do it this way. And the Trusted Computing Base is everything that you need to be secure for the system to be secure. That includes basically all the core parts of the OS itself, CPU changes or CPU privileges, permission systems, memory protections like we've talked about, device input and output, authentication, cryptography, and so on. Okay, TPM, right? All the stuff that we've talked about, reference monitor. That stuff has to be secure for the security policy of the system to be secure. Anything that's not the TCB is everything else. So, you know, libraries, modules, applications, code that doesn't involve permission systems and so on, display, all of this stuff. This stuff can all fail or be compromised, and it won't compromise the whole OS, okay? So let's say a particular user program gets Trojaned. Well, it might be able to steal your data or corrupt your data, but it can't actually take down the whole computer, right? The only way that, like ransomware, for example, usually doesn't crash the whole computer because the user doesn't actually have ability to, encrypt the OS. Ransomware encrypts the data that the user has. So that's terrible for that particular user, but unless there are other security vulnerabilities or issues, it shouldn't be able to take over the whole system. So it's helpful to think about a system that you're designing when you have to think about security. Think, what is in the TCB of this system? And then I really need to focus on that particular part, security. The non-TCB part of the system, yeah, security can matter. We don't want users to be able to hurt themselves or delete their data, or we don't want it to crash and corrupt data, but it cannot, those things that are not in the TCB cannot affect the overall security of the system. Okay. Then some design principles for trusted operating systems. You always want to make security easy or mandatory. Otherwise, people are going to circumvent it. If it isn't easy to do the right thing, people are going to find ways to do it the wrong way. Any trusted system has to have the principle of least privilege throughout the entire operating system. So at the very least, you need permission systems with different levels. Permissions can't be optional. This is sometimes called discretionary access control. If a user can get out of doing something the right way, they can make things insecure. So for example, on your home computer, of course it's natural that you can switch into administrative mode and install things or change things. but that means that that system isn't truly secure because you can break it. But in a more managed environment, users don't, like in the computer lab or whatever, you don't have access to do whatever you want to those machines. And so the system is secured against you or against malicious code that you might accidentally run. So you want to be able to have permissions and think about ways to make enforcing those permissions mandatory. The next idea is economy of mechanism. We talked about this before when we talked about secure software design. You want things to be as simple as possible and no simpler, right? So necessary to implement everything, complete and correct, but use less code, use functions, reuse modules. That's going to help your systems be more secure. An example of this, right, is our reference monitor. One security system to rule them all, so to speak. Least common mechanism is a security speak way of saying minimize ways that information can be shared between users accidentally. Okay, so user A shouldn't be able to see or know what user B is doing because that's a security risk. That's pretty easy to understand, but you frequently have to you frequently have to do things to make sure that users can't see what each other's programs are and what they're doing and things like that. So you just have to be thoughtful about it. Open design is always recommended for trusted systems because in order to understand and analyze a system to know whether it's really secure, you need to be able to understand its design. So if it's a proprietary system, it's going to be harder to do that. And finally, again, complete mediation. We really want to be able to check every access of a system when possible in order to make sure that the security properties are being enforced correctly, even check to see if the properties have changed and so on. If it's not possible to do complete mediation, for example, that would be too inefficient, then we need to make sure we have clear and documented behavior so that people understand how things work. All right, that's what I wanted to say today about trusted operating systems. So thank you.